In this video, we're going over the derivation of equations of motion in one dimension for constant acceleration. Let's start by defining all the terms necessary. The first which is position. Position is the coordinate that is measured from the reference point. This reference point is what you think of as the zero of what you're measuring. Position is also what you use in a graph. However, displacement is the change in position. In this case, it is the x in the final coordinate subtracted by the x in the initial position. Distance is all the length accumulated in the path. In this case, we define d by the sum of all the little length along this line. Another very important term is velocity. Average velocity is defined by displacement divided by the change in time. Average speed is distance divided by the change in time. It's very important to distinguish that these terms are not the same. Another very important term is instantaneous velocity. It is very similar to average velocity, but the only difference is, in this case, we take the limit of the change in time close to zero. We call this the time derivative of x. Knowing this, we can also define the instantaneous speed. It is the size of the instantaneous velocity. In this case, it is absolute v of t. We're going to define another term called acceleration. The average acceleration is the change in velocity divided by the change in time. Now we can also find the instantaneous acceleration. We end up with taking the limit of delta t close to zero. So it is the time derivative of velocity, and it also equals to the time derivative of position. Now we end up with another term called the second derivative of x. Now I want to go over some important intuition in calculus of why are these terms related to the graph. This is a graph of position and time. Now let's zoom in on this x1 position. If we define the point x2 and a line between them, this length is the change in time, and this is the change in position. And the ratio is the slope of this line. As delta t gets closer and closer to zero, this becomes closer and closer to the instantaneous velocity at that point. And it also becomes closer and closer to the slope at exactly that point. This is why velocity is the slope of the position and time graph. Let's take a look at the velocity and time graph. Considering from the change in position divided by the change in time is equal to the average velocity, we can say that this tiny change in position is equal to the average velocity multiplied by the change in time. In this case, it is the area of this rectangle right here. If we were to sum all the tiny areas in this graph, then take the limit as delta t gets closer and closer to zero, and then the number of rectangle gets closer and closer to infinity. This is exactly the definition of an integral. Integral dx is the final position subtracted by the initial position. This part right here is the integral of v dt from the initial time to the final time. We have concluded that the change in position is the integral of velocity respected to time. Here's what we got so far now. And unsurprisingly, if we do the same for the relation between v and a, we'll also get that the slope of the v graph is acceleration, and the area under the curve of acceleration graph is the change in velocity. And now we have the complete relation between position, velocity, and acceleration. You can find each of them by using integrals and derivatives. Now let's start deriving some equations for constant acceleration. Let us look at the relation between velocity and time. We can see that the slope of this graph is acceleration, which is equal to the change in velocity divided by the change in time. In this case, it is v of t subtracted by v of 0 divided by t. And now we move a to this. Now we have our first equation of motion. Now let's consider this graph of v and t. From what we know earlier is the area of velocity and time is the change in position. So we can straight up find this area right here. So delta x is equal to v0 plus v of t divided by 2 and then multiplied by t. This is our second equation right here. Let's move on to the third equation. These are the first and the second equation. Let's try substituting the velocity from here. This is our third equation. Again, from our first equation, we can manipulate some stuff. Let's substitute this into our second equation. And this is our fourth equation. You might notice that it is quite similar to the conservation of energy equation. That's another great way to remember it. This is a summary of all equations that we found today. You might have been familiar with them through what they call the SWOT formula, which might make these equations easier to remember. Now this part is for those who are familiar with calculus. We're going to derive all the equations by using integrals. Let's start by the definition of acceleration, and then we can integrate this. And it goes from the initial velocity to the final velocity, and the t initial to the t at final. So in this case, the acceleration is constant, so we can pull it out of the integral. So we have the conclusion of our first equation. Before we will find the second equation, let's start by asking what is the average velocity. In this case, with constant acceleration, it can be thought of as just the change in position straight up divided by the change in time. But it also can be the initial velocity and the final velocity divided by 2. So we'll have the average velocity. Now from this, we can see that if you move the term delta t to the right side, we'll have the second equation. This is our first equation. Notice that we can write velocity as the derivative of x. Now we can integrate this. Now we'll have our third equation. Now for the fourth one, we start off with the definition of acceleration. Now we can separate this using chain rule into two terms. Notice that this chunk right here is velocity. So we'll have a equals v times d by dx of v. Now we can integrate this by dx. From x0 to x of t. So we'll get on this side so the domain is changed from x of 0 to v of 0 and this to v of t. And in this function we'll get v squared over 2 evaluating from vt, subtracting v of 0. So this right here is delta x, and here we get v squared over 2 subtracted by v0 squared over 2, and now we'll finally have the fourth equation.